Welcome back. So we are on chapter 13. We're just going to do this chapter and then one more, chapter 15, and then you'll be done. So let's see what's going on here. So we're going to get in Newton's law of gravitation. So this is less of new content and more like we're going to actually apply it to things. So we're getting into some Newton's laws, some variations of what Kepler did with Newton's laws, etc., and other physics, math, a lot of geometry stuff. So we're going to be talking about gravity, and I know this chapter specifically is going to be geared more towards physicists, I would say, than engineers. And I would say that it's not as useful from an engineering standpoint. It is more interesting than a lot of the other physics stuff. So even if you're like, I'm not going to use this in my future, I'm not going to calculate the rotational velocities of galaxies or anything like that. It is very interesting. It's a lot more interesting than, how fast is a car going next to a guy on an escalator or something like that. So anyway, you'll see what I'm talking about here. So we're talking about gravitational forces, or specifically gravity. So there's a big question, a big mystery of like, where does gravity actually come from? We know that the more mass something has, the greater its gravity, but we don't truly know where the force of gravity comes from. And this is actually one of the last great mysteries of physics. So me as a physicist, the research that I've done is not truly physics research. The research that I have done is more material science. So the research I've done is high pressure, high temperature physics, and it's looking at certain materials, the transitions it goes through, the properties that change, like the electrical properties. Does it become an insulator? Does it become a conductor? Does it become transparent? Like metals become transparent, this kind of thing. So it's more of a material science-based thing, but physicists are actually running out of pure physics research to do. But like I said, gravity is one of the last great mysteries. This will be a really big deal if somebody can solve or even figure out just the smallest direction in which to head in to figure stuff out about this. Okay, so obviously a lot of these things listed on here are pretty obvious. Obviously, gravity holds us on Earth. It keeps the Earth from flying out of orbit from the sun, stays in orbit with the sun, all this other stuff, galaxies, etc. This is actually pretty interesting too. They have like this pulls the supercluster towards the great attractor. So the theory was always for a very long time that there was a Big Bang. So there was a singularity, meaning that is an infinite amount of energy in a single point in space. And basically this single point blew up for whatever reason. This was the birth of the universe, right? Everything's flying out, and as you've already learned in this class, it has some amount of kinetic energy forcing it out, right? So it's being pushed out. Everything's expanding. So the idea was always that as everything expands, as we know it and we see it every day here on Earth, that kinetic energy will run out. It can't be infinite. It has to be conserved. So as it comes across various things and it slows down and the force of gravity starts to pull on it, things will go out, slow down, eventually stop, and then be pulled back into each other. And again, crush into a singularity, and then you'll get the birth of a new universe. And so for years and years, scientists thought this was the way things happened. Crushed into a little single point, blown up, whole universe, crushed into a single point, and it's just this repeating cycle over and over again. Since then, we figured out a couple of odd things, like really odd things. So we look at the farthest points away from the center of the universe that we know it as, and we can only see as far as light has traveled to get to us. So the universe would actually be bigger, especially in certain directions, but we don't actually see it because the light hasn't actually reached us yet. So we say that the age of the universe is 14 billion, 13.5 billion, something like that, um, billion years, right? So it has taken that amount of time for the farthest reaches of the universe's light to reach us. Um, there's still light hitting us every day that's coming from farther and farther away. So we learn more about the universe every day, because every day the universe gets a little older from the point of the light hitting us. Um, the interesting thing is when we look at the outer edges of the universe, these things, they must be slowing down, right? They're running out of energy. Um, the problem is they're not. They're just not. There are things that are actually accelerating out from the center. So they talk about this great attractor. They say, okay, well, there must be something that is attracting these galaxies that are being pulled outward. So there's something beyond our sight that they're theorizing. It could be other things, but the main idea is that on the outer reaches of our universe, there is something else. What that is, we don't know. And then you can let your imagination run wild, right? This is where science and physics gets really interesting. Like, what could it be? So basically, there must be something larger out there that these galaxies are accelerating towards. There's something with even greater mass that is making these things attract towards it. So really interesting. What we call so if you have, basically you start out with, I'm going to say this is a solar system, right? So within your galaxy, you have like a bunch of solar systems, right? And they're possibly all rotating like so. But then you have other galaxies, right? So you have other systems of solar systems, whatever it may be. And just to make it different, we'll make it rotate the other way. Oops. And then, of course, these things must rotate around each other somehow, right? So they're spiraling around each other. So everything is winding around against everything else, right? And then you call these, they call them local superclusters or whatever. So the Milky Way is a part of a larger set of galaxies that are all orbiting each other. And those larger pieces that are orbiting around other superclusters. It all comes down to the idea of the center of mass again, right? So we have all these individual planets that are inside these solar systems, like right here, and then these solar systems are all a part of a galaxy. This galaxy is moving as a single entity. There's a center of mass, and that center of mass is rotating around another center of mass, say over here, and then these things have a center of mass within them. It's all from your perspective of where you're looking, right? Okay, so there's some other things in here. We could talk about this stuff all day. I'm sure you don't want to get that into it, though. So we're using technical terms like stuff. The term dark matter, if you've ever heard of that, dark matter is not actually a thing per se. Basically, they have just using the same physics that you've learned now, and they said, okay, a galaxy is rotating like this. Therefore, if we use the physics laws that we know and we apply the formulas, it should have this much mass. But when we go to actually look at it and we add up the individual pieces, it's missing mass. It's missing a large sum of mass. It's not like 1% or something like that. It's, I think, upwards of like 40% missing mass in certain galaxies and whatnot. So they say there must be some other mass. We're missing mass. So the missing mass is actually just an unknown variable. And this missing mass, they've just decided to call it dark matter. Because it's out there, it must be out there. Because these galaxies must follow the laws of physics, right? But we don't know what it is and we can't see it. so we say it's dark. It must be some dark matter. Um, that is not to say that there is some invisible matter out there that's affecting things. All it is, it's like a variable x. It's an unknown. We don't know what it is. So whatever this stuff is that's controlling gravity, we say Earth has lots of stuff, right? Earth is made up of a large mass, so it has large gravity, so things are attracted to it. Force is always attractive, never repulsive, as far as we know. Gravitation then is the tendency for bodies to attract each other. Again, you're aware of this in everyday life, right? Then we have Newton's law of gravitation. You can define the forces between them, and we think of gravity from the standpoint of we are on the surface of Earth. We are always attracted. Gravity is always acting downwards. If you were in space and you are here and some other person is over here, you're going to attract one another simply by whoever has more mass. Eventually, one person will actually rotate the other person, right? Because you're going to basically be falling inward towards that person and then be pulled around by gravity. You're constantly falling inward, essentially. If you have equal mass, then you're just going to orbit each other. So it's all a perspective, and the point being that as you change the masses so that they're closer together and not so far apart, it makes more sense. Because right now we're saying the Earth, of course you're attracted to the Earth. But if you change the masses of the particles, then it becomes something more of a question. So we get into some of the equations. You have Newton's law of gravitation. When it says mass 1 and mass 2, these are two of those things that you're comparing. So if it's you and your buddy, you can be mass 1, your buddy can be mass 2. If it's, for instance, the Earth and the Moon, then the Earth can be mass 1, the Moon can be mass 2. It's just two masses that you're comparing that are orbiting each other or attracted to each other in one way, shape, or form. The radius is then just the radius between them, right? So you have object 1, and then you have object 2, and then you just have whatever the radius is in between them. The G, this is also an interesting concept. So the more familiar you get with math, the more you can truly start to understand it and realize what's happening here. So we have equations. You have force equals mass times acceleration. Basically, when we make an observation on Earth and you take the mass, you take the acceleration, you can figure out the force, or interchangeably depending on which variable you know. When we do experiments, we do observations, when we apply that equation, exactly what we predict will happen happens. This is how we know this equation works. Essentially, when you throw in a constant that is not just, say, because like mass can be a constant also. If you know what the mass is, it's then a constant. Until you know the mass, it's an unknown variable. But this gravitational constant is always this value. This is what the sort of the probably truer definition for you that hasn't seen a lot of this stuff. It is a constant, right? This is always true. It is always this value. So what is actually a constant? A constant is essentially, they'll refer to it as a fudge factor. So essentially when we look at something, we say, okay, someone went mass 1, mass 2, it's this radius, it should equal this force. But it doesn't. It's off by some value. And then they said, okay, well, let's look at two different masses. We'll look at, say, the sun and the Earth. And we compare these things, we do the radius. Again, it's off by some factor. And what they figured out was it's always off by this value. So essentially the equation that we figured out is not a perfect equation. It is not the exact value of what we're looking for. But we can make it pretty much a perfect approximation by figuring out exactly the factor that it is off by, which is this gravitational constant. And the approximation gets closer and closer by how many decimal points you add to this, and it gets more and more accurate as you up the precision of that constant. So meaning the decimal places that you add to it. Um, so pretty interesting that the formula we figured out is actually not the right formula. This is not the perfect formula that solves the force between two objects that are orbiting each other or in gravitation proximity of each other. But by adding the constant, it becomes perfect. So it doesn't matter that this isn't the perfect equation. We've figured out a way to make it a perfect equation. So whatever. It's sort of like some things you probably never really thought about. Might be kind of mind-blowing. You may not care at all. You may just say, I just want the mercenary method, whatever it takes to get the job done. That's fine. The force always points from one particle to the other. So again, you have this vector form. So this is the unit vector over here. I think we talked about that earlier. And then, yeah, we talked about the rest of it. So they get into this shell theorem. I don't know how useful this is for you per se, but basically they're saying Earth is a nesting of shells. So various shells, so like a hollow sphere is a shell, right? Just the inside's hollow. And then you take a sphere and then you put a smaller sphere inside that. That's also hollow, and another hollow sphere, etc. But essentially what you can do is, like we talked about before with the weird shaped masses, if you find the center of mass, then you can break all it down into a single point. And it doesn't matter the shape of it anymore because you know the center of the mass, and then we can treat it as a point particle. Essentially, that's what they're doing here. And the force pairs they're talking about, again, is between two different particles, 0.1, 0.2. We're talking about little dots between each other, but this could be anything, right? This could be, again, two human beings. We've just broken down the mass into a single point, and we're going to relate them to each center of mass. So again, they're talking about the 2 points. In this case, are an Earth, or the Earth, and an apple. So it doesn't matter if you're looking at it from the perspective of Earth to the apple or the apple to the Earth. They both exert the same force on each other, which is this 0.8 newtons that they're talking about. So, difference of math, the Earth acceleration. Again, they're just pointing out, again, that it doesn't matter which particle we're looking at, whether it's the tiny particle or the giant particle, they are exerting the same force on each other. It's sort of again, we're looking at like Newton's third law stuff here. So we have a particle is to be placed in turn outside four objects, each of mass m. So again, we're looking at a bunch of spherical shells. They all have the same mass. A large uniform solid sphere, a large uniform spherical shell, a small uniform solid sphere, and a small uniform shell. In each situation, the distance between the particle and the center of the object is d. Rank the objects according to the magnitude of the gravitational force they exert on the particle greatest first. So again, exactly what I just said. It doesn't matter the size or shape of something once you break it down to the center of the mass, right? You break it down to the center of mass, and then you treat it as a point particle, which basically means, again, all these should be the same, right? All exert the same force on the particle, so it doesn't matter. Okay, so we're getting into Newton's second law and the equations that we're using here. The book breaks a lot of these down more if you need to know, like, oh my god, where did this come from? But we can see the force here is, again, and they're not going to write mass 1, mass 2. It's just going to be like basically larger mass, smaller mass. A lot of times the mass differences of things is so great that the second mass is irrelevant. It adds so little information that it doesn't actually really change the answer. So if you're, for instance, doing the sun as particle 1 and Earth as particle 2, the mass of the Earth is so insignificant compared to the sun that it becomes irrelevant. You can essentially do one mass. But the difference between them has to be very great. You wouldn't want to do this between even, say, yourself and like the space shuttle. or since we don't have space shuttles anymore, the space station, right? The space station's a lot heavier than you as a person, right? But still, the difference isn't too great that you probably want to eliminate the data you would by eliminating your mass. Okay, so we get this acceleration, and essentially what they're saying is what I just said here. We basically eliminated this smaller mass because the information becomes irrelevant. But you can also do just the acceleration from a single mass if you just want to know it by itself. So we could do just the Earth and not look at anything else compared to it. So this gives us the information that we're used to. And we can see here that the distance they're talking about is this radius. So that's the farther you get away from the center of the Earth. We have the magnitude that they're talking about here. And then, so when we've talked about things in labs and stuff, we've pretty much talked about the surface of the Earth. And from the point on the surface of the Earth, gravity is more or less measured the same everywhere. Only when you get to extreme places like Mount Everest being the tallest place on Earth does gravity begin to change. You're getting far enough away to make it a little bit different, a little measurable difference. They have very precise instruments that can measure just the slightest variation in gravity. That's not the kind of thing we're talking about here. But you have to get pretty far away to notice a difference. So they're talking about the highest balloon that's ever gone into the atmosphere. It's gone to 9.71. The space shuttle, while it's in orbit, is actually 8.7. So every time you see those guys in space and they're floating around, whether it's in the space station or the old space shuttles, they are not actually weightless per se. They are only weightless in regards to their relative thing that they're in. So that's the space shuttle. They're actually constantly falling. So it's like a skydiver that's constantly falling. The space shuttle is falling towards the Earth constantly. It's just in constant free fall. Communication satellite is much farther away, and then like a GPS satellite is in what you call geosynchronous orbit. So most of the time, the Earth rotates like this, and satellites just whipping around at a different speed. A GPS satellite is actually in geosynchronous orbit, which means it rotates at the same rate. So a satellite that is here, say this is pointing directly towards Florida on this side of the globe, it always points towards Florida. So it's like the moon. It always faces the exact same spot as it spins. The GPS satellites are much, much farther away, so the effective gravity is much smaller. Okay, so the calculated acceleration, we talked about this, different places it is. The Earth's mass, it's not uniformly distributed, but we treat it pretty much the same because the variations are so small. For most things we're doing, it doesn't matter. If you are doing some kind of experiment that is highly sensitive to gravity, you would obviously want to measure where you are. The Earth is essentially spherical. We treat it as a sphere most times, but is not a true sphere. Obviously, again, like when you look at Mount Everest, that is a much higher point than, say the lowest points on Earth. The Mariana Trench in the ocean, this kind of thing, the lowest points on Earth. Very big difference. So it's a very big difference of mass between those 2 points. The Earth also actually rotates. So you have, let me see if I can remember this. So you have the mantle, or the Earth's crust, and then we'll make that a small, thin layer. Then you have the Earth's mantle, which is larger. So you have, let's see if I can write this here, mantle, you have crust, get back to my middle school science, and then you have the first core, yikes, and then the second core. And this core is liquid. So, and the reason that this core, the first core, is liquid is because the great temperatures, right? So the temperature increases as you go towards the center of the Earth. It increases so much that it melts everything within that section of the Earth's layers. The interesting thing is that the temperature is even greater in the center, but the pressure is so great it has solidified the mass that is inside that. So it's no longer liquid, it becomes solid. And it's actually fascinating because it's more or less iron at the center, and it's become essentially a solid sphere of iron in a molten iron liquid that's traveling around it. So the iron, which is just a big iron sphere ball, can spin in the center, and because it spins, it creates a magnetic field around the Earth, which is where we get the magnetic field. So it's all actually pretty fascinating how the interiors of the Earth work, what it does, what it creates. The magnetic field protects us from like the sun's radiation, etc. So all pretty interesting how things have turned out for our planet. Difference in gravitational force and weight due to the rotation. So again, sort of the record player instance where you have the bug on the outside versus the inside. If we're looking directly from top down on the Earth, where the North Pole is at the center, it's not spinning. You're going to get these differences. So you have this angular velocity that we talked about, the theta over t, or the change in theta over change in t. And you can get the acceleration out of this and the gravity. So again, normal force in this case, if we're looking at the surface of the Earth, is then just gravity, right? It's the opposite force, looking the other way. Remember those lessons from way back when, the box on the inclined plane and all that stuff. So you get these forces. And back to the shell theorem again. We're talking about the forces between the elements do not disappear, but their vector sum is 0. So again, you have something sitting on a table. It has normal force going up, gravity going down. The net force on them is then 0. So again, we're talking about this solid sphere, not a shell. More of the same stuff. Again, they're talking about a constant density. Obviously, the density is not the same around the Earth. Depending on if you're looking at, like, the ocean. The ocean is obviously way less dense. A particular region of Earth that's heavy in metals compared to rocks, the density is going to change. But we just assume a constant density, and then we look at the mass in 4/3 pi r cubed, looking at the volume of a sphere. And then you're left with this equation. So they're matching the equations in here to get this. And then essentially what they're doing is, we talked about this earlier, the gravitational constant is just a number. It's a number that they figured out, fills in all the missing blanks in the equation. You have a mass. Whatever mass that is you're looking at, once you figure out what it is, it's a constant. The larger mass, again, same deal, constant. The radius, once it is measured, is a constant. All these things are constants, right? So we can just say that once we have all these things together, we multiply them to divide them, it's just a single number. Whatever that number is now a singular constant. We'll just call it k for argument's sake. When we look at this then, this is just simply Hooke's law, right? So you have some constant times some vector. So when we look at an object dropped to the center of the Earth, if you say you have just a hole that goes to the center of the Earth, when it goes down through, if this is the opposite end, this is the starting side, this is the opposite end. When you drop it through, it's going to go through, and then it's going to pass the center, and then forces are going to pull back on it. So it's going to go back like this, and it's going to bounce back and forth until eventually it just oscillates at the center and just stays at the center of the Earth. Because again, all forces pulling on it equally, it must stay at the center. So we'll start talking about gravitational potential energy, right? So you've learned this so far as MGH in a lot of cases, right? This is your gravitational potential energy. This is the spring stuff you would have done in the lab, etc. But we're looking at it between two particles. So this is not necessarily the case anymore. And intuitively, on a small scale, things aren't going to work out the same way, because you think to yourself, I'm picking up something, I've increased the gravitational potential. If I drop it, it's going to have a larger impact into what it collides into. It becomes a bit different when you're looking at things from an astronomical standpoint. Things are getting so far away that the gravitational potential is changing in a much greater fashion. It essentially is becoming weaker and weaker as you pull it apart. So they're talking about you can't split it and say what belongs to what. Again, from the perspective of standing on Earth, the Earth is much larger, so we're like, the Earth is always pulling this thing towards it. But when you start getting into things very far away, same deal. You can't really say how much belongs one to the other. Gravitational potential energy of a baseball. It's just an example they give. Kinetic energy, again. We're just going to move on from this. So we're going to get into the potential energy. And we see it's this same deal as we did before. So if we look, this is G small m big M over R squared is then the force. So this equals force. So if we go back and we look at this, G over big M, small m, exactly the same, except now it's R, and now it's negative. So you may or may not be at this point yet, but you're going to start to recognize mathematical stuff. And this is what I was saying like in the early lectures. People that are already very good at math, you can fake being good at physics. So you don't actually understand what's happening, but you can recognize this immediately. When you have this situation, if we take the derivative of this is just a constant. We're going to bring R up from the bottom. So it becomes R minus 1. You take the derivative, you pull down negative 1 in the front. We'll just do this like a d/dr thing. You pull this down in front, so you're going to add or subtract 1 from it. So then this just becomes negative 1 over R squared. So you can see all we're doing is taking derivatives and integrals to go back and forth between the force and the potential. So they are related in this fashion, right? So again, as E against negative, we just showed Y. The value is negative and approaches 0 for R as it goes to infinity. So as R goes to infinity, potential goes to 0. So again, a little different than when you're on Earth and you're right here and you're dealing with a couple feet, you pick something up, you know it's going to smack into something harder. When you're dealing with these huge distances, as it gets farther and farther away, the potential goes to 0. It's not quite the same. And then we have the potential here, and similar thing here. You have mass 1, mass 2, mass 3. Again, it's a system of particles. We can add them up and find the potential. More the same from previous chapters. Again, the work done is path independent. It doesn't matter which path it takes, as it follows the whatever line it wants to. It can wiggle, goes to it. All we want to look at is the starting point and the ending point, right? And then we're going to look at that. This is exactly what I was just talking about. Gravitation can be derived from potential energy by taking a derivative, right? We just talked about this. Again, at rest, infinity, kinetic energy equals 0, and potential equals 0 because R is approaching infinity. Again, these are theoretical situations. Obviously, it can never reach infinity, but you get into situations where things are so far apart that we say it's more or less infinity, right? This is a million light years away from this thing or whatever. It's more or less infinity. So you can just sort of make these arguments to figure out possibly a problem you're working on. So again, you're getting the kinetic and the potential. We take the classic kinetic that we already know, 1/2 mv squared. with the new potential that we now know for these planetary orbits, and then you can figure out a velocity for this, right? And then they're talking about rockets, so rockets are really big with this. If your planet is rotating this way, if you launch something in the same direction, you already have that benefit of the rotational velocity it's already moving at. I think it's been a while, but I believe the escape velocity needed to leave Earth's orbit is maybe 13 meters per second. It's either 11 or 13. I think it's 13, maybe 13.2 or something like that. But they take what they can get wherever they can get it. So if you can get a little bit of a boost going the same direction as the Earth, you get a little bit of boost, right? They also do it, so they know they're going to do it to the east. So they also want to do it over large bodies of water. So when they drop things, or in case something goes wrong, something explodes. This is why specifically they launch things from like Texas and Florida. Texas, you have the Gulf of Mexico out there. It's a large body of water. Going to go to the east, out over there. Florida, obviously, you have the whole Atlantic Ocean. Going to go east, large body of water. And now we're looking at various planetary bodies. We're looking at their masses, their radiuses, and then the escape speed it takes. So, it's 11.2. So it is listed here. It was 13 or 11. So it's, I guess, 11. So, but the escape velocities become much harder, or much higher as you get to the planets become larger. So if Jupiter had a solid surface, it doesn't. It's a gas giant. If you were to land on it, you would have a really tough time getting off it. It's, it's almost 6 times the required the speed to get off it, right? And it's kilometers per second. I was thinking meters per second didn't make sense, but okay, that makes more sense. So yeah, 11 kilometers per second. So yeah, you would need a whole lot of chemical propulsion. You would need extremely large rockets to get off this thing. It would be bad. So you move a ball of mass m away from a sphere of mass larger m. Does the gravitational potential energy of the system of ball and sphere increase or decrease? Is positive work or negative work done by the gravitational force between the ball? It should be negative work. You're pulling them apart. And does the gravitational potential energy of the system of ball and sphere increase or decrease? We just talked about this earlier. So it'll increase because you're pulling them apart. And like I said, the negative work. Okay, so now we're going to talk more specifically about Kepler's laws. So again, more interesting stuff. I don't know how much of this you'll use. It's good information to have. It's fascinating how, for such a long time ago, how people figured out this stuff. I guess this is what happens when you don't have smartphones and television and all this stuff. There's literally nothing else to do. Okay, so one of the interesting things, and if you follow, which I don't, I would not suggest it, but if you follow astrology, that's with an L, not an M, not astronomy. Do not get those confused. That's very embarrassing. But if you follow astrology with the L, it'll be like Venus is in retrograde this month. So, you might act a little crazier or whatever nonsense they talk about. Retrograde is a real thing. At least they thought specifically it's what planets did. Retrograde is when something is going through a normal orbit in a circular or elliptical fashion, but then all of a sudden it looks like it does a little loop inside the loop. So it's going around, it goes loop, and then keeps going. So all of a sudden, for no apparent reason, the planet or the moon, whatever it is you're looking at, is suddenly going backwards in direction, which makes absolutely no sense. And they couldn't figure out why this was happening because it just appeared that that's what was happening. So you can see here that it would look like a planetary body was moving in this direction, and then all of a sudden it would be going backwards, and then it would be going forward again. So they would call this retrograde, and they couldn't figure out why. again, Johannes Kepler, Tycho Brahe, fascinating stories between them. Um, one essentially being the understudy or grad student, I guess you could call it. Um, and you can see what's going on here. And then this just gets into the laws. We'll get into this in a minute. But this is the breakdown of like the geometry of an ellipse. So you have 2 points here and here, which help you define the ellipse and the parameters of it. You're going to get some radius from it. You have a radius or a distance between the two bodies that you're talking about. And we'll get into more of this in a second. So again, defining some of the terms that they're talking about. This is actually Kepler's first law. All planets move in elliptical orbits with the sun at one focus. So obviously he's talking about specifically our solar system. This is like a weird thing. You'll see it especially in like science fiction movies and stuff. Like they'll go to a different solar system and they'll say, you know, oh, look at that sun. It's not that sun. Sun is just the name of our star, so there's only technically one sun. But they will use this term a lot for other solar systems, other stars. They'll say, oh, the sun in that solar system. It's become a weird thing. It's just used more and more. Most people aren't going to pay attention to it except, you know, scientists and people that do this kind of thing. But anything orbiting a star or the largest mass in a solar system must move in an elliptical orbit. It's just sort of just mathematically impossible that it moves in a perfect circle. So the eccentricity, which is defined by this E, is the measure of basically how circular something is. So the closer it gets to a perfect circle, the closer it gets to zero. The farther it gets away and becomes an elongated ellipse, the closer it gets to 1. So the eccentricity of Earth is actually extremely circular with this value approaching 0, right? It's a pretty good circle. If you get something like comets that are coming in and whipping around, like these really long things, it's going to be closer to 1, right? It's the opposite direction. And then we're talking about these semi-major axes, which was in the previous slide, these axes. The second Kepler's law is that basically we'll get rid of some of this. We'll say sweeps out equal areas in the plane in equal times. So if we make an ellipse like so, and you make the sun one of the axes, if we look at the physical two-dimensional area it's covering, and say we look at this time interval right here, whatever time it took to get from here, we just started timing, we're watching this thing go by, and then we stop the time. It took some amount of time. If we then look at it on this side and we say, okay, we're going to start timing it right here, it's going to appear to cover a much greater linear distance in the same amount of time. It's going to be something like this. But in reality, when you measure the area between whatever the moving object is in your reference point, it's sweeping the same amount of area. So this is very thin here, right? But this is very wide. If you were able to go through here and measure this like square meter by square meter, this equals the same amount of area as this. Obviously, I just drew it by hand. It's not perfect, but that's what they're talking about. It has to cover the same amount of area in the same time. And then this is more of a mathematical law. The first two are kind of intuitive. You can kind of understand them by visually or conceptually looking at something. This one is a law of periods. It's saying the square of the period of any planet is proportional to the cube of the semi-major axis. So it's more of a mathematical thing. So they're talking about again, capital T is usually defined as the period. The square of this is then the cube to the semi-major axis orbit. So the semi-major axis is then, they're using the sun again here for this. And then we're saying the radius is this. It must be cubed, and then period must be squared. So it's more of a mathematical one. So again, you have the semi-major, various, using different points as the semi-major axis. You Mercury, Venus, Earth, etc. The period it takes, and then basically this third law that is out here. So you can see that when you take t squared over the radius cubed, they all equal roughly 3, right? So that's where, like, Kepler came up with this, right? He's like, oh, you know, like, I look at these various planetary bodies, and, you know, when we take the cube over the, or the square over the cube, you know, they all equal the same thing, or roughly the same thing. Satellite 1 is in a certain circular orbit around a planet. We'll make a little picture here. Satellite 1. That's terrible. Satellite 1. While satellite 2 is in a larger circular orbit. So, larger circular orbit. Satellite 2. Which satellite has the longer period and the greater speed? So, the greater speed, again, we're looking at like kind of the record player deal here. So the larger orbit is obviously 2, and then the greater speed has to then be 1, which hopefully makes sense without much explanation. Okay, so now we're getting into the energy of these things. Okay, so you get this same GMM over R. You say, okay, where did the 2 come from? I believe in the book, if you look at equation 13-37, if you look at the algebra done, it should be pretty obvious where that comes from. But then we're just we're using the kinetic energy here, and then we're saying, okay, so this portion is equal to potential energy, right? We can pull this out. So it's just, the kinetic energy is just 1/2 of the potential energy, which is kind of interesting that it comes out that way. But it also comes out that way because you know you can interchange the potential and the force by taking the integral and the derivative. So it's somewhat intuitive if you're familiar with the math. So you get the total mechanical energy, again, is like we learned before, the kinetic and the potential. So you get these two pieces, and then when you combine them, basically you're getting a circular orbit, right? So basically this thing being 1/2, this being 1/2 of the other. So this is being a whole, so it's like a half minus a whole is just going to equal negative 1/2, right? So the total energy is the negative of the kinetic energy, which is what we just did. So for an ellipse, substitute A for R, which we kind of did that earlier. So they're saying all these orbits have the same energy, right? So we just elongate this ellipse. And then as we get circular, right, changes the radius, kind of this semi-major axis compared to the radius that we're looking at. And then we can see the differences in the kinetic energy and the potential and the total energy, etc. Okay, so Einstein and gravitation, getting even farther away from your engineering needs as you go into futures as engineers. The general theory of relativity. So there's the special theory of relativity that came up with Einstein came up, and then he came up with the general theory of relativity. So basically we're talking about things that are relative to each other. If you were inside this box and you had a scale inside and you measured the acceleration of gravity, you wouldn't know what's happening outside the box. And essentially what this is saying is if you were on Earth, it would read 9.8. then if you could be in space and being propelled by some rocket and just happen to have the same acceleration at 9.8, that it would seem like you're still on Earth. So you wouldn't know actually that you were on Earth or in space in a rocket. To you, from your point of your reference point, it's the same, right? You can't tell the difference between them. And these are some sort of conceptual ideas that they came up with to help explain space-time and how it's curved. You may have seen one time or another on Discovery Channel show or on YouTube these days, this guy right here. So a lot of times they'll use a large rubber sheet and it's just flat, and they'll pull down the ends of it, and they'll take something like a bowling ball and they'll set it on the rubber sheet, and you can see it deforms the rubber sheet to make it bend inward, like here. And then they say, okay, we'll take a marble or something and we'll roll it around, and you can see it goes around this rim, right, until it slowly falls in and it hits the bowling ball. That's essentially what they're using this sort of conceptual device to explain how gravity's working in space-time. So it curves inward. If you look at something like a black hole, and there's no way I'm going to be able to draw this, but similar thing to this up here, where you have this circular pointing inward, only now as it curves inward, it just goes infinitely down. So it has no stopping point. So where this stops right here, that becomes the place where you measure gravity. Where a black hole goes, this goes just infinitely inward, because you things that approach the radiance or the radius of no return, which I'm not going to get into all that. You can't come back out. Even light that bends inward towards it, they can't get out, right? The effect of gravity is essentially infinite. It's a singularity inside that black hole. But what they're talking about here, they're talking about analogies in A and B. Paths appear to be parallel along the surface of the Earth, and you can see they actually converge. And then we can see, again, our point of reference as you step outside the curved Earth. We can look at it and we can see curved space. Okay, so one of Einstein's theories was not able to be proven, I believe, was the general theory of relativity, and I think he came up with it in, I want to say 1919 or 1921, somewhere around those couple of years. It couldn't be proven, and they said, okay, well, whenever we get the next solar eclipse, we can look at, and solar eclipse is then when the moon passes in front of the sun, right, and it blocks out the sun. So whenever that happens, we can look at the edges of the moon and see if light is actually bending around the moon, and that'll prove whether this is true. Because when you get into these crazy theoretical stuff of trying to figure out whether it's real or not, it becomes very hard to do an experiment about it, right? So they figured out a good way to do this, and the problem is that the solar eclipses they don't pop up too often, and when they do pop up, they pop up on only specific places on the planet that you can see them. So it might be like once every 40 years that we see a solar eclipse in the United States, but you get a solar eclipse every few years or whatever. So I believe in 1938, give or take, might have been somewhere like in Bulgaria or something, I think, they were able to travel there and use these ancient cameras to take pictures and to actually record the gravitational lensing is what it's called. That's when you can see the light actually bending around an object that's so large it's able to affect the light. And then they were able to prove this again with modern, I think in like modern telescopes and stuff, and larger objects in like the 90s, I believe. So just kind of reinforcing that it is true. But basically you have a large object here that they're talking about, and you can actually see that light is coming in this direction and actually bends around the planet inward and then continues on its path. which again, with this pen, I can't really do this. That's a little better. You can see it bending inward. And then if it bends totally around something like this, you can see it bending in, every way. They call it a ring, right? It's something behind it. There's so much light behind an object that it's all bending in a circular fashion. Again, we don't know what actually causes gravity. Is it something in the mass? They've theorized that there is actually a particle called a graviton that is it is a part of matter. If that's true, then we could get some really cool things. We could start to manipulate these gravitons and change them, and then you could probably get things like floating cars and hoverboards and whatever, but nobody knows. And even if we discover that such a particle exists, it'll be probably hundreds of years before we figure out how to manipulate it. So I wouldn't count on like the Jetsons happening within your lifetime. And that's it. So again, not a whole lot of engineering related stuff, a lot of very interesting things from like a Discovery Channel perspective and things that are happening. So yeah, hopefully you thought it was interesting. But yeah, as usual, get back to me if you have any questions.